Deep anesthesia is used for neuroprotection in severe brain diseases, but it is associated with postoperative complications as well. The authors of this study investigated interstitial ion homeostasis and the role of sodium-potassium pump during isoflurane anesthesia. Ex vivo rat brain slices were exposed to isoflurane at moderate, that is 1%, and high, that is 3%, levels. High-level isoflurane, relevant for deep anesthesia in vivo, substantially increased extracellular potassium, but reduced sodium concentration and synaptic transmission. Similar changes in ion concentrations were also observed when blocking the synaptic activity and 2-pore domain potassium channels, suggesting an ion redistribution mechanism independent of neuronal activity and potassium leak conductance. When seizure-like events were induced in brain slices, although isoflurane considerably lowered the incidence of such events as expected, the duration and spike count within these events increased with increasing isoflurane dose, accompanied by delayed extracellular potassium clearance, suggesting increased excitability. A delayed potassium clearance and delayed sodium normalization were observed during and after spreading depolarization as well. Cortical stimulation in rats showed similar results as in the brain slices. The extracellular potassium clearance time constants almost doubled during deep isoflurane anesthesia, characterized by the burst suppression pattern, leading to interstitial potassium accumulation. Potassium distribution and clearance are regulated by the sodium-potassium pump, also known as the sodium-potassium Atpase. Using a coupled enzyme assay, isoflurane was found to specifically impair the astrocytic neuronal isoforms of the sodium-potassium Atpase. In computational modeling, 35% sodium-potassium Atpase inhibition increased extracellular potassium and led to prolonged potassium clearance and membrane depolarization, mimicking the effects of high-level isoflurane. This was verified by sodium-potassium Atpase inhibition in vivo, which resulted in burst-like activity. This study provides a novel mechanism by which sodium-potassium pump impairment could generate cortical hyperexcitability during burst suppression and contribute to neuronal dysfunction after deep isoflurane anesthesia.